Here's the middle section of our COED talk. After we've established the importance of the cerebellum as a key integrator in so many aspects of vision, and we've also talked about how eye movements are connected to so many parts of our body, from our feet to our ears. Now we'd like to do a deep definition of the triads, the big three, the three cerebellar areas of interest, three semicircular canals, planes of movement of those canals, three planes of the otolith movement system, three image stabilizers, the three foveal directors, and the three vestibular ocular reflexes. Let's go ahead and begin. So the big three are really vestibular, visual, and somatosensory. These are the foundation of neurological function. It's sort of the foundation of what we are and how we cope with gravity, and how we have our maps of ourselves and how we interact with the things around us in life. The three things we learned as cerebellar are the ABCs: accuracy, balance, and coordination, but there is so much more, as we pointed out. We're going to talk about the areas of interest in the cerebellum, the floccular nodule, the flocculus or vestigial region, oculomotor vermis, the FOR and OMV, the flocculus and paraflocculus, and then the uvula. Now, these, when the first anatomists looked at these, they look very much like the back of a throat. So just to help us visualize, we'll call the vermis, the worm, the top of our palate, that real line, the top of our palate. The uvula, of course, that little punching bag at the back of our throat. And if you can feel around the tonsils that hang down from the side, that's the anatomist embodied that. I think it'll help us remember this. Those three areas of interest are really brought up with Ariel Shemesh, and particularly David Z., the great granddaddy of cerebellum at Johns Hopkins. He talks about the three key areas: the tonsils for the high frequency vestibular response for smooth muscle maintenance and steady gaze holding; the uvula, that's low area response, is going to be for more of the otolith system; and then that top of our mouths for saccades, and then, as we know, for convergence. How these things are all interconnected and in our performance with our motor system. So just remind you about the semicircular canals activation triangle. The pitch, yes, yes, yes. The yaw, no, no, no. And the roll, ear to ear, very much like the XYZ of an airplane. And how these semicircular canals are hardwired to the eye muscles that are associated with their plane of motion, and like the horizontal canals with the lateral and medial rectus. We've got the obliques, and I won't go through it in detail here, but the key thing is that each canal excites a pair of muscles and inhibits a pair of muscles in its action plane, its action vector. So let's do a little canal simulation just for fun. I went ahead and put this together so that you can help remember this. We'll call this our ability, and I appreciate Dr. Joe Hatch sharing this. So what we're talking about is, think of the canals go back like this. So we have, this will be our posterior canal, our anterior canal. What do we think most about? The horizontal canal. So here's the posterior canal, right? Posterior, anterior, horizontal. And then these two are going to be the otoliths. We've got the saccule, goes up and down, and the thumb, the utricle, that goes side to side. So that's what we'll be thinking about as we go back and forth with this, as we look at the area of movement. And so, of course, when we want to make a canal movement, as we go to the direction of plane, of course, that side is going to be activated and the other side is going to be turned off, inhibited a little bit. It's this push-pull system in both directions. And the horizontal canal are associated with angular acceleration according to the head, okay? And it's, again, hardwired to these link muscles, in this case, the muscles of the lateral and medial recti. Now we look at the anterior canals. Think of that anterior here. Again, as we move it down, both canals, they both activate. I'm not talking about the eyes now. We're just talking about the canals. And then back up, we can do that to the right or the left canal. These are these areas that require acceleration to get the endolith going and connect that. And of course, those are connected with the two muscles that are associated with vertical movement and then inhibited on the other side. Posterior canal, we'll think of that posterior. That's of course going back and left and right. Again, same type of thing. We're going back, and that's our posterior canals. And of course, these work in tandem. So the route plane is the right anterior, left posterior movements. And that's associated as we get into VORs and how that stimulates the different canal movements as we tilt our head in the different directions. Now, this is actually a plane of action degree, and I would suggest as we trace our nose back and forth, or think of where our nose would be, that's going to stimulate all those planes of motion. Generally, the horizontal canal, to get the maximum isolation, we go ahead and move it down again. So the idea is, in a real life, all these canals are almost working together. But if we isolate them, we find an area of difficulty, we can isolate that particular plane and help rehabilitate it. Now, the otolith system is associated with the rocks in our head. We all have rocks in our head, and they're on all the time. They're pushing down all the time. And so this is very much like a boxer. The bob up and down, like a Bob Pepper trampoline band, weaves side to side. And everybody at the gym knows lunge movement, forward and back. And these systems are very interesting as far as how they're placed. There's only two of these organs. They have a macula. And so I would suggest this macula needs to match, of course, connected to the macula of our eyes, and how the utricle goes the forward and back, left to right, and the saccule is the up and down, the one we get in our elevator feeling. And again, these are all associated with translational movement and linear acceleration, as well as just basic as we are stationary. At this point, as again, our right tilt is the same as a left acceleration. So there's some ambiguity that has to be figured out in those higher brain functions. And that's why we love roller coasters. We can be tricked a little bit. I think it's interesting when you look at this, the amount of striola on the macular side, those little sensors, and how much of the utricle is on that medial side. And you notice how that, even the saccule is pretty much up and down, that the utricle has that interesting tilt that helps us, again, disambiguate this issue. And remember, they're always on, and they vector together. They represent really the X, Y, and Z axis possibilities for our whole body as it fights gravity. And those lateral and medial connections, all those arrows, essentially, when you look at all those vectors, that's going to correct all directions of gravitational motion. Here's the other interesting thing that's associated with us, that stimulation of the torsional eye movements. So these are also responsible for the roll and counter roll that happens as we move our eye, as our tilted side to side. So again, another access point for activation of and making sure our therapies work better. Now go to the three eye movement systems, and I think you're more associated with this, but just quickly to review, the three that direct the fovea: the saccade system that brings that image, the one that has some volitional control; pursuit, that holds the image when it's slower, and then the vergent system that moves the z-axis up close and far away to keep that image directly on the fovea. Saccades, of course, are externally guided and can be internally guided, and so can be associated with too fast of a pursuit, or a quick, or a sound that makes our attention go to a certain area, and also again is suppressed as it moves. And then the internal guided saccades really connect with our frontal area, so we do memory, these anti-saccades and memory guided saccades associated with higher visual functions, an access point to train higher visual functions and maintain higher cognitive functions. And of note, the eye movements have two classes, slow and fast. Just like we have fast vergence, slow vergence, we also have thinking fast, thinking slow. Kahneman, who just passed away. And slow movements are more pursuits, but as it speeds up, it becomes a saccadic movement. And saccades are just happening all the time, 2 or 3, sometimes 2 or 3 times a second. It can be hundreds of thousands a day. And they are a great source of information on how we process things in our visual world. As we think of pursuits, again, it's more of the parietal, and you make a pursuit to your right, and then, of course, it's right brain activity. Now, of note, again, it desiccates over to the cerebellum on the other side. So we get this idea of that cerebellar connection. But in the case of pursuits, it goes just like you'd think about your side vision, where the side vision is. Go to the right, that's a right. Right pursuit is a right brain, right parietal affect. And then, of course, the vergent system is our domain. We think about that all the time. Convergence, maybe as we learned about, maybe it should be convermus, as we are using the vermis to cross our eyes as well as control other things. Eye movement systems for steady fixation. Of course, fixation is really the foundation for all movements. You have to fixate well, or these other systems don't work well, and that holds that object in a sensory, stable position. Again, the eyes are constant motion, but it holds it within that field of understanding. Of course, the ocular vestibular system, it holds it during brief head movements. The optokinetic system holds it with sustained movements. We're not going to get into the optokinetic system today as much. Just be that ocular system is associated with a reflex, the VOR, and that central vision is just vital to keep our attention. And instead of having neck muscles like birds, we have to use this other system. And it's so important. Infants seek eye contact. We prefer that. Fixation is so meaningful as a developmental part of cognition. And without fixation, we got a problem, as we found in autistic children or children that are blind. Just do a quick assessment. We've talked a little bit about, or the other session talked a little bit about the circuitry of the cerebellum, which is elegantly simple compared to other areas, and that's why it's used so much. But the key thing to be aware of is that granular, as we've talked about, all the granule cells that grow that first year in life, those beautiful Purkinje cells that Purkinje identified for himself. And then it goes up to that context area of the parallel fibers and those beautiful climbing fibers that execute learning with their complex spikes. I thought it would be best, this was just done by Dr. Raymond just a couple of weeks ago. She did a wonderful job from Stanford explaining this, so we're going to turn some time over to Dr. Raymond. Dr. Raymond?
And that's this question of what is the algorithm a neural circuit uses to implement learning? What are the rules that determine which synapses change in response to a given experience? And, what is the logic that determines whether you tweak, let me put on a pointer. What is the logic that determines if you need to change your output to an input? When do you tweak this synapse versus that synapse? And I'd argue that there's no circuit in the mammalian brain for which we really understand learning at this algorithmic level. So my strategy has been to choose a circuit that has a relatively simple circuit architecture that makes analysis of this question easier. And of course, that is the wonderful cerebellum, which has just 5 main types of neurons in the cerebellar cortex, plus a couple of others that are smaller in number. And as many of you know, there's been like a surge of interest in the cerebellum recently, and that interest, like throughout neuroscience kind of interest, and that's come in great part from the wonderful work that's going on showing increasing evidence for a role of the cerebellum in all kinds of functions that were previously ascribed solely to the forebrain. Things like navigation and attention and planning, fear, and social behavior. So lots of complex behaviors and very cognitive behaviors now ascribed to the cerebellum. So I'm a big fan of that work, but that's not what we do in my lab to get at this question. we've sort of chosen some of the very simplest forms of learning that are implemented by the cerebellum. We study oculomotor learning, so that's how visual and vestibular inputs drive eye movements, how the cerebellum contributes to the commands for eye movements, and how cerebellum-dependent learning can alter the eye movement response to a sensory input, a visual or vestibular input. And then we leverage the simplicity of the circuit and the behavioral system to try to connect the dots between what's happening at the synaptic level, at the circuit level, and at the behavioral level during learning. And today, I'll tell about how in trying to connect the dots, we stumbled upon evidence for two kinds of metaplasticity at the cerebellar synapses. First, in the first part, I'll talk about threshold metaplasticity, so experience-dependent changes in how hard or easy it is to induce plasticity. And in the second part, I'll talk about plasticity of the timing rules for plasticity. So changes in threshold and timing requirements for inducing associative plasticity in learning. And in both cases, we'll be talking about the classic parallel fiber to Purkinje cell synapses. And I'm sure you're all familiar with this textbook model of cerebellar learning, but I'll take you through it and then map oculomotor learning onto this. So as you know, Purkinje cells are the sole output neurons of the cerebellar cortex. You can think of them as representing all of the different responses the cerebellar cortex might want to make. The parallel fibers carry very rich information about context. They're getting input via the mossy fibers and granule cells about coming from all over the brain. And then the other main input to the Purkinje cells is from the climbing fibers. So Purkinje cells represent responses, parallel fibers represent the different contexts in which the cerebellum might want to make those responses. So by modifying the appropriate parallel fiber to Purkinje cell synapses, the cerebellum could learn to make the right response to a given context. And the plasticity at these synapses is under the control of the climbing fiber input to the cerebellum. If you record in vivo, the climbing fibers seem to encode errors. Sometimes they encode other things as well, but they, in many contexts, seem to encode errors. And so the cerebellum is thought to induce this climbing fiber-driven depression through this big calcium influx, inducing associative long-term depression of the parallel fiber to Purkinje cell synapses, and thereby weaken synapses that contribute to errors. So that's the textbook model. We, in our lab, have been considering the extent to which this model can account for oculomotor learning. And oculomotor learning, we're looking at smooth eye movements, changes in smooth eye movement responses. The goal, so the Purkinje cells in the flocculus that controls oculomotor learning drive eye movements. The goal of the eye movements is to stabilize images on the retina, and so if there's image motion that represents an oculomotor error, that error is encoded by the climbing fibers, and that can weaken visual or vestibular parallel fiber synapses that caused a bad eye movement. So that's the model. We've been asking how much of the oculomotor learning can be accounted for by this. We think some of it can and some of it cannot. In particular, in the first part of the talk, I'll be talking about the vestibulo-ocular reflex. So vestibular signals via the mossy fiber granule cell parallel fiber pathway provide vestibular signals to Purkinje cells. The Purkinje cells can drive an eye movement response. So as shown here, if the vestibular stimulus that we deliver is rotation of the head about an earth vertical axis, so like a left-right head motion, that vestibular stimulus, so it goes left, right, this is the head velocity. The eye moves in the opposite direction, right, left, and then By pairing the vestibular stimulus with a visual stimulus we control, we can induce a learned increase in the VOR. So if we pair the vestibular stimulus with oppositely directed image motion of an optokinetic drum, after about half an hour, we see a learned increase in the eye movement response to the vestibular stimulus alone. If instead we move the visual stimulus in the same direction as the head, then we can induce a learned decrease in the eye movement response to the vestibular stimulus. So we can alter the amplitude of the eye movement response to a head rotation in either direction, an increase or a decrease. And if you record from the climbing fibers, which I did when I was in Steve Lisberger's lab, and compared responses during a bunch of different training conditions, the climbing fibers encode errors during both kinds of training to increase the VOR and training to decrease the VOR. However, a number of lines of evidence suggests that this LTD, climbing fiber triggered LTD mechanism, contributes selectively to VOR increased learning and not.
So we think about LTD, that depression. So the Purkinje fibers in the cerebellum is the brake for these movements, and she just did a great job of identifying that main workhorse for all these researchers, the vestibular ocular reflex, the VOR triad. So we're going to go in that a little bit depth right now. I'm going to go ahead and identify, because it's identified a number of different ways for this talk, and maybe in the future, we'll talk about the three different types. I'm going to call the side-to-side horizontal, even because that's often used versus the other angular directions. So that will be the horizontal, even though it is also angular. And it can be overridden by, as she mentioned, by a VOR cancellation, where you go ahead and as you hold as it's stimulated, you're holding your image to fight against that eye movement to the one direction. We'll go in this with more depth in a second. Key thing right now is to realize that that's what we're identifying. We're going to call the next the AVOR, or angular. Also, another used often is rotational. In other words, anything that has a rotation, particularly around the neck, and it can be the body too, is a translation or an angular VOR, and that stimulates, again, the semicircular canal, and also can be canceled, just like the other example, just in a different direction we'll use. And the third thing, which is really exciting, is the translational, or other words, linear, sometimes used, VOR. And that's connected directly to the otolith organs. The neat thing, that also can be canceled or overridden with that TVORX. So here's our nomenclature to understand the horizontal, angular, and translational. And just remember that's generated by head-body movement. It has to be moving for the semicircular canals to generate information. Some people suggest that it would release dopamine. And the otolith organs on each side is always on. It's not associated with movement, and it has to do with linear input, up and down, bob, weave, and possibly is associated with serotonin after a few minutes. So a quick system and a slow system, as Dr. Z has said. Of course, I always just learned really just the one system when I was going to school, Dahl's eye reflex, which can happen while you're unconscious, and you can, again, use it to identify different areas of the lesion. But remember, it was developed in utero with the vestibular fibers being myelinated at 24 weeks, one of the first myelinated systems going. And as we are in the womb, we are, in a sense, they would suggest that we are using our Dahl's eye in these type of reflexes way before we are born, 28 weeks. And it's not dependent on any type of visual stimulus. You can be again, unconscious. Other way the therapists look at this has to do with using the motion portion. An X1, they suggest the head still and the eyes move. We would call that, of course, a smooth pursuit movement. An XO, where the head and eyes are locked together in tandem, we'll call that a cancellation, a VOR cancellation movement. And the third thing is an X2, as we've just discussed about how you can, gain up a system. And that's what I would say a VOR plus pursuits, opposite direction, right? Opposite pursuit. So I'm moving my VORs, turning on, but I also adding even a little bit more, turning it off and adding a little bit more with these XO, X1, X2 clarifications for therapists. Here's a wonderful calendar that you can, again, a directionality chart that talks about the direction of the head and the direction and what's activated. And you notice that what activates the cerebellum on the right and left side, the LARP and route planes. This is available, again, online. Truthfully, just like the Park 3-steps test, sometimes I have to go back and really think this through. I think if this is not natural to you, you didn't learn this in school, just having something like this will help you know, as I move my head in a certain direction, these other things happen. And this is, again, in a chart form that connects with the muscles. So nose right is the right horizontal canal, right? And that's going to be the right medial rectus and the left lateral rectus. And the eyes, as I move to the right, as my head moves to the right, to compensate, the eyes go left. So all the different directions that you can play around with, hopefully understand. Now, this is an interesting thing that's found in my gym as far as a Z Health trainer. This is a VOR chart that I use every day when I train. I move my head back and forth. This is not just for neck movement. This is to stimulate the canals and the connection to my eye muscles. I think it's a powerful thing that should be just as important as a heart chart. And as we look at these different directions, you can use, these things to identify. So here let's look at the VOR. So I'm going to go and move my head to the right, and my eyes move to the left. Now, if my right canal is stimulated, it's going to, even if I'm not, something else, if I was to stimulate that directly, my eyes would move to the left. So this is very much like the patellar reflex. And I think this need to be very comfortably part of what we do and understand. We're going to go over this again. This is going to get better and more in depth as we talk about this with a number of different researchers from Reza's lab. Guy did a great job. I think you'll really love this as a connection with autistic children. Guy?
And so in this reflex, there is another structure that is extremely important. So you have the VOR, but you have the VOR that is here. It's the 3-arcs loop that is extremely fast, as I said, but you have the cerebellum that will modulate the amplitude, so the gain of this reflex. And so a very specific part of the cerebellum has been shown to be very critical there. It's the flocculus. I will talk about floccular complex in the talk. And so briefly, I will. I know you know this one, by heart. But basically, there is two main excitatory inputs in the cerebellar cortex. One coming from the mossy fibers that will excite granule cells. Granule cells give rise to ascending axon, and then parallel fibers that contact Purkinje cells. Purkinje cell is the only output of the cerebellar cortex and can also be contacted with another excitatory input that is the climbing fiber, the famous error signals and teacher signals in supervised learning. That is one of the strongest excitatory inputs in the brain, actually. And there is a gigantic literature showing that the plasticity between parallel fiber and Purkinje cells is critical to modulate the vestibulo-ocular reflex. So yes, while we are looking at the VOR, well, for the reason I just said, it's well conserved, very quantitative and reproducible, and it's easier for translational studies with kids. But also there are evidences that are actually not clear when you look carefully in the literature, but there are evidences that potentially vestibular system is more active in ASD children. But it's also, usually they didn't try to correlate it with the mutation, and if it was a gain of function or loss of function, so it was always very hard to interpret. But therefore, because we have seen that potentially there is a vestibular gain that is more active in in ASD patients, therefore we decided to build our own system. So here it's the control test Kilo 1. it's Maggie Bender, actually Kevin's daughter. And we built a very simple system. So we basically bought a helmet. We put an inertial system on the head with gyroscope and accelerometer. And then here we put a small spy camera here to track the eye, infrared camera. And here you can see the image, and we perform the tracking of the pupil and the corneal reflection to have the reference of the eye movements using deep lab cuts. And so to quantify our VOR, we do a VOR gain, that is basically the ratio between the eye movement and the head movements. Here is an example of the head movement in purple. It's inverse, so it's inverse because usually they are anti-correlated, but just for illustration, I inversed it. And here you have the amplitude of the eye movement in dark. And here it's for very kind of slow, not very slow, but kind of slow head movement oscillation, because the temporal frequency is 0.4 Hz. So basically it's 4 cycles in 10 seconds. So again, this is what we got with neurotypical example. So the gain is around 0.5, 0.6 or something like this. However, when we started to test SCN2A loss of function kids, we were surprised by the very high amplitude of the gain. It's the same experimental conditions, same room, same day. And so basically you have a way higher eye movements, compulsory eye movements when you turn the head almost for the same amplitude. And what we decided to quantify a bit better. So here it's per cycle. It's neurotypical. As I said, we have around 0.5, 0.6 in gain. So it's the ratio between eye movement and head movement, remember. And here for SCN2A loss of function kids, the gain was basically 1. It was like saturated. It was really high. So then we decided to test if it was also the case in mice. And we use SCN2A heads animals. So basically we have the mutation, you have only one allele that is functional to mimic the haploinsufficiency that you observe in SCN2A loss of function. And we basically...
So you get an idea of how exciting this is, that there is a difference between the children with autism and children with neurotypical, and how that's something that can be trained and changed. And he suggests that there's a hypersensitivity in those autistic children, or those in the spectrum. And then, of course, with some knockout mice, he duplicates that. The other thing that Guy said that I hope you realize, that he talked about the sensitivity to children for vestibular input. So, and then he's sort of leading to, why doesn't someone apply this clinically? Who's going to apply this clinically? We're the people that know, if we know how to gain up and gain down, can see how this can affect these children's lives. Just one other interesting note on another, just before he started this, he talked about how a friend had some new pairs of glasses playing tennis, and how it changed the gain and how it took him a while to reset. And he said there should be some way of using glasses to change the gain also. These are things I've actually emailed him to let him know that there are people doing this. These are things that just in our area, I'm hoping this gets you as excited as it's getting me. So we're talking about changing the VOR gain. As he said, that's plasticity system. And so let's just do it all together. Again, we can gain down by keeping our eyes. We'll give you some more techniques on this, side to side, and gain up. Gain down, gain up. And of course, when we did this at the conference, it turned out very effective. I think hopefully that's the one thing people learned. Now let's talk about how that's applied. Generally, when you go through the system, you start with mice, then humans, and then start applying optic genetics, which is really isolating the circuit. And so I'd love to have this comments here from Rez's lab.
It is nice to see that when you induce learning in these modules, indeed, you do see that the activity goes up. To reveal or show you the prominence of the VOR adaptation, you see this owl in which you do not only see stability of the eyes, but also the head. So the cervical ocular reflex is also controlled here. You see that's a very powerful reflex and important to show you to keep the target in space and keep your gaze stationary. Now, we can mimic this reflex in mice in our lab. So here you see on the right side, you see a pupil moving with respect to the corneal reflections first in the dark. So then you measure the VOR, the vestibular ocular reflex. And then during the training, for example, you can give an out-of-phase stimulation of the table rotation and the visual rotation. And when you subject the mouse for like half an hour to the stimulus and then put them back in the dark, then you will, of course, see that due to the increase in retinal slip, which changes the climbing fiber activity, then you will see a change in the gain, in the amplitude of the eye movement. And there are many possibilities to vary this over time and space and so on, but I'm just taking this very simple paradigm for today. So here you see the pathways involved. So the brainstem, the floccular Purkinje cells get input from the vestibular ganglion cells through the floccular projection neurons, and then the Purkinje cells themselves target the floccular target neurons that in turn then inhibit the abducens neurons so that the eyes can go to the lateral side when you move the head to the opposite side, or let's say to the ipsilateral side. If you record, for example, from the left flocculus and you turn your head to the right, then the eyes will, of course, move to the left, so everything is sort of stabilized in space as much as possible. And so this, we predict simple spikes will go up during this kind of modulation. And when we recorded this was indeed what we saw. So you see that the gain can be increased. And when you record from the left flocculus, you see that the number of spikes per second is increased very simply in relation to the gain. Now you can say, okay, well, this might be an epiphenomenon, but maybe it's just a sort of efference copy signal. It's not a causal effect. But then when we induced and used optogenetics to stimulate these Purkinje cells in isolation, as we did here in this experiment with Kai Folks, then indeed, dependent on the strength of the stimulus, we could stimulate and increase the simple spike activity accordingly. And then based upon these different stimulus strengths, we could indeed get a different eye movement amplitude in a virtual linear fashion. And so this was really caused by stimulating the flocculus. And so we think that an increase in simple spike activity really can be causal to an increase in the gain of the compensatory eye movement.
So again, with this epigenetics, he was able to ramp up and really prove that there's this very, very important pathway and we can exploit it. Mm-hmm. So we talked about this. What is the most common or most prevalent system that's trying to change our eyes? Is it attention? Is it the frontal lobe? No, it's actually the vestibular system. There's almost 1 million action potentials going on as the right side screams to pull the eyes to the right and the left side screams to pull the eyes to the left. Huge amounts of energy. And that makes it just such a quick trigger draw as we move our head. The vestibular system can turn on, and to keep that gain close to 1, even though, as we've just pointed out, in an ideal situation, it's less than 1. Over 1 is more an autistic child. But we're going to, again, investigate that a little bit further as we talk about the neurocircuits and how they contribute to eye movements. Now, this Venn diagram is very important from Dr. Z, and the idea of mostly diagnosing things with problems. You notice how that these Venn diagrams, in the center, we have smooth pursuits and misalignment. These things all connect there, and with the 3 areas of interest, saccades and the gaze holding. But that smooth pursuit is such an important part of our system, and understanding, of course, when somebody has a brain injury, why that's the thing that doesn't work. We can override it with our saccade system sometimes. And maintaining that accurate performance has this robust adaptive capacity, and it responds to change. And I love this comment: unless you see your patient within seconds of neurons insult. Seconds, any abnormality will affect not only the immediate damage, but the attempt of the cerebellum to repair it. The cerebellum within seconds attempts to repair things. What a great system to understand and utilize and exploit in our therapies. The second concept, that the retinal slip is that error signal that conveys up to the inferior olive. Remember, the inferior olive is the teacher of the Purkinje cells, and that's what drives this circuitry. Just a quick overview, the nervous system does three things: receives that afferent system, decides what to do with the input, and then creates a motor output. And we are more oriented towards survival. The brain survival process can be summed up in two words: pattern recognition or prediction. If we can actually predict, that reduces threats, risk, and pain because we know what's happening next. And this brain activation, the brain's feeding patterns, it needs electricity and glucose, but chemically is 10%, electricity is 90%. Our brain needs interaction and electricity to keep on and keep growing. And these things that are active together, wire and fire together. I think we all understand that concept. Second main job is for movement. Like Sherrington said, that movement is that final common pathway. And the example of a sea squirt who has a small nodal cord brain uses it to go to a good place to sit down, and then it just absorbs the brain. Without movement, we don't need much of a brain. And of course, we have this great spot. The retina is the only part of the brain that moves. So we can truly exploit this, not only just for eye movements, but for all neuro activity. And the eye should be looked at as this coupled joint that needs to be explored and enhanced. You think of VR, and mapped and continually remapped. Inaccurate sensory inputs can be assessed by immediate change, sometimes in flexion and extension. And we know when someone is feeling bad, when there's inaccurate feelings, that's what we call that motion sickness. We call that an affect issue. And if we're very skilled at this, we can see that as we do our therapies, what it helps and what hurts. And of course, the cerebellum is that important place where the inputs are stored, learned, and corrected. That air system corrected, and that has that cool homunculus, just like our motor system and sensory system at the top of the brain. On old Olympus towering top, a Finnan German viewed a hawk. I was taught, in old Olympus towering top, they took the cerebellum and cut it off. We never learned much about the cerebellum in my anatomy class. We didn't learn this either, location of why the different eye control muscles are separated in these different patterns. And I would suggest that, of course, the ocular motor number 3 is more of a flexor affect and circuits. The trochlear nerve is, I could call, a superflexor. Again, that's that down and in. And the abducen is that way down at the bottom of the pons. That's the extender, because the pons and the cerebellum are extender areas. So this idea of in and out is reflected in the three locations for our nerves, ocular motor nerves, and then of course that cerebellum is that great extender. Let's talk about the three different areas again that we've hit on. That FOR, FMV. Think of our Harald palette, accurate during acceleration and deceleration of smooth movements, smooth pursuits. So you think about that. We need to make sure if this is a problem, we should be doing that acceleration and deceleration. That's where that activates the best. It talks about saccades, using saccadic activation, and activates with convergence. It's associated with speed adaptation and learning. Then we think about the tonsils off the side, the flocculus, paraflocculus, we've talked so much about. Essential for holding eccentric gaze fixation, not eccentric fixation, but eccentric gaze fixation off to the side. And then it has to do with the pursuit maintenance. It is the smooth pursuit area, the flocculus and paraflocculus, the smoothing of the pursuit. It also modifies the gain with that angular VOR. And also very closely associated then, of course, with that gain about the VOR cancellation. That has to do more with directional adaptation. So using again, speed adaptation and directional adaptation, two different areas. If there are two different areas, we should exploit it as two different parts of our therapy. And the last, the nodulus and uvula, maintaining and generating that linear or translational TVOR, it's an otolith triad, controls the velocity storage mist, and then it's associated with slow angular VORs and downward pursuits. As the VOR slows, it no longer stimulates the endolith, and it has to transfer back over to the rocks, the uvula system. This wonderful chart from Z Health, I'm hoping that you get just a chance to look this over. Should be a part of just in your background, so you really understand these areas, because if we understand the division of the cerebellum, we can exploit that in our therapies. That's where we should divide our task into those parts. And so the FOR, again, that just to simplify, the vestibular oculomotor region speeds up the eye movement going towards the opposite direction and slows it down coming towards it. And so we think of saccades, and again, we think a lot about convergence. And so this is a great diagram, talks about the acceleration and deceleration. And of course, we can augment that by forcing it to do something it doesn't want to do. But you think about, this is a convergent system. Look where it's going, down and in. That's what accelerates. That's why it's so important to understand that and how it adapts for different speeds. Then we talk about the flocculus and paraflocculus. The key thing about that is it's associated with the horizontal and anterior canals, but not the posterior on that side. It's for fixation, smooth pursuits, helps our eyes move in opposite directions, and keep those VORs in check. Be aware the flocculus is, again, associated with inhibitory. As Jam taught me, Jam Gajar, the eye is always on, and then this is the brake. This is the brake that keeps us in the present and our sensory area in the right location. And so look at these directions. Again, the side to side and the upward direction, as well as these interesting downward positions that are associated with more maybe a torsional movement. So again, the flocculus, paraflocculus, we need to exploit the directionality of these systems. And who better to talk about this is Mike Golden, who really taught me just an excellent job. So Mike, if you can go ahead and explore this.
So remember our vestibular influence on eye movements, where when I turn my head left, it activates the left horizontal canal, which ends up pushing my eyes to the right. But like I mentioned, it's trying to do that every second of every day. It's all about the balance. And when I shift the balance, that's when the eyes move. If I turn right canal gets activated, it gets to win, and my eyes go left. For the cerebellum, if we're talking about gaze fixations, you have the flocculus. You have a right one, you have a left one. The right one is connected to the right side of the brainstem, left side to the left side. They are connected. Again, this is connected to the stuff that's going to the eye muscles. It doesn't actually connect to the canals. It's connected to the relays going to the eye muscles. It's connected to the arrows, the push. My right flocculus is connected to the stuff that my right canal is talking to. The left flocculus to the stuff that the left canal is talking to. And the connection is inhibitory. So let's say, for example, that I wanted to stare to the right. I want to do gaze fixations to the right. What would make that easier? It would be way easier if that right canal was not trying to push my eyes in the opposite direction so much. So my right flocculus upregulates its inhibition to shrink down that push, and that's so much easier for me to look to the right. Again, see the balance between the arrows. This is way easier for me to stare to the right without my vestibular system trying to fight me on it. And so the cerebellum inhibits to make it easier. Now, if I wanted to stare to the left, well, wouldn't it be nice if my left vestibular system was not fighting me on this? So my left flocculus activates to inhibit this push, And again, hopefully you can see from the arrows, it would make it much easier now for me to stare to the left, because my left vestibular is not fighting me, because the left flocculus calmed it down. But now what happens if this isn't working correctly? Let's say my right flocculus isn't doing its job. I lose this inhibition. This arrow now gets bigger. If I try to stare to the right, this right vestibular signal is now really fighting me. And you're going to see exactly what you saw in that gentleman from the video yesterday. Drift and bounce, drift and bounce. When he tries to look to the right, because again, the cerebellum is not helping him any. That inhibition was needed and it wasn't there. If instead the problem were on the left side, I lose the inhibition here. Again, that balance of arrows is not going to be very conducive to trying to stare to the left. I try to do it, and I'm going to keep drifting back to the middle because that arrow is so big. The same process is then involved in smooth pursuits. If I want to do a smooth pursuit to the right, again, think about which arrow here would fight me if I were trying to do a smooth pursuit to the right towards that R that you see on the screen. It's going to be that purple arrow. So wouldn't it be cool if that purple arrow weren't in my way? So the right cerebellum kicks into gear to help me do a smooth pursuit to the right. If, however, it's not working and I lose that inhibition, this arrow gets real big. And now, when I try to do a smooth pursuit to the right, that purple arrow is going to fight me. And so my eyes are going to go too slowly, meaning they're not going to keep up with the target, and I'm going to have to do catch-up saccades. I'm going to have to jump my eyes to try to catch up because the vestibular system is fighting me too much. And so it'll look like this. Jump, jump, jump. Because again, the cerebellum is not helping me reduce the drag. Similarly, if I want to do a smooth pursuit to the left, left cerebellum shrinks that down, and so much easier. If it's not working, I lose that. I lose the inhibition. Now there's going to be a lot of drag. The eyes are not going to move fast enough, and they're going to have to jump to catch up.
Mike's an excellent teacher. Again, as somebody that's didn't learn this in school, it's been very, very helpful. So I appreciate Z Health's help in allowing us to share this. I hope you noticed also this is directionality specific. And how many times have you noticed someone as they're smooth pursuing, as soon as they get to the center, it's sort of a bobble and goes to the other side. This is where this occurs, right? And just remember that this has to do with the directionality of this, and that the neurons, again, often favor initiating and going other directions. So the one side favors the one direction, the other side favors the other in this push-pull fashion. So if we find that there's a weakness on one side, we could immediately start thinking about exploiting that and concentrating our efforts in oculomotor control on the one side. And just this comment at the bottom, torsional smooth pursuit cells in the flocculus are most sensitive to pursuit to extort the ipsilateral eye. So Samantha, here's a great thing we should be exploiting by isolating and using these muscles to do well. Second thing is the nodulus uvula. We're going to talk a little bit about this a little more in depth, but remember the triad of movements is always on, associated with downward smooth pursuits, and it has that velocity storage mechanism as we move our head. But remember, it's always on and works in coordination with the semicircular canals, particularly when they slow down. So we're going to go ahead and just finish this pre-test questions we did when we started. First one had to do with using a reflective movement when we want to have our eyes move down and to the left. So you think about that, that's the same as if I move my nose up and to the right, my eyes are going down and to the left, up and to the right. So that's an AVR drill for the right posterior semicanal. That's the answer for that first question. Second question had to do with the boxer going up and down. So we think of up and down now. I think you have a pretty good idea. That's Bob. Sacuole. And so we're thinking about the otolith system. And what is the otolith system does? A slow VOR drill. Remember, slow would not activate the others. And with the anterior canal with a downward smooth pursuit. So a slow drill in that anterior direction. So if I need to work going up, that's the same as my head going down, right? That's what's happening. And then just a downward pursuit on top of that. And the last thing has to do with the left shoulder and hip turned in. That indicates that the left side has a cerebellar weakness. And so what stimulates the cerebellum? Complex nonlinear body movement, but because of it's on that left side, with the left side fixating on that target. Those two things together, combining movement with fixation directionality, is something we use in the Z Health gym and as a Z Health trainer all the time. So we'll now be going to the next section on applying cerebellar circuits. Thank you so much.